Hello, everybody, and welcome to this NASA Google Plus Hangout. I'm Karen Fox at NASA Goddard Space Flight Center in Greenbelt, Maryland, and we're going to be talking to you today about what happened on March 29th. On March 29th, the sun erupted with an X-class solar flare. A solar flare is this burst of energy and light and X-rays that the sun sends out into space. And this particular flare was the most comprehensively observed flare of all time. We are going to be talking to you today about 5 of the observatories that saw it. We're really going to be focusing in on those 5, but actually there are even more than that saw it. So when everybody found out we had one of the best data sets of all time, the scientists got so excited. Everyone said we're going to be learning more about flares than we ever had before. But what's really exciting for us is that these observatories also took some great pictures. So we're going to be sharing those pictures with you. We are going to be talking about why this is exciting. And to start off, we're going to go to Lucia Kleint, who is going to be telling us the story about how this great data set was even coordinated to begin with.
Thank you, Karen. So the whole story actually started last year when several collaborators and I wrote a proposal to the National Solar Observatory, and we asked them for observing time. So we were very fortunate to get 10 days at the Dunn Solar Telescope at Sacramento Peak in New Mexico. And then we wrote another proposal to NASA's IRIS satellite and NASA's and JAXA's Hinode satellites to ask them to join us for these flare observations. So once we arrived at the telescope, we spent every day tracking sunspots and waiting for flares to happen, and of course waiting for good weather, when one day we saw this active region which got bigger and bigger and had the typical magnetic field which favors flares. So we decided this is it. We told Hinode and IRIS to please point there the next day, and we did the same. So when we arrived in the morning, we pointed our telescope at this active region, and we got really lucky because X flares, the large flares, are quite rare. So in our display, suddenly the sun got brighter and brighter, and we just couldn't believe it. It didn't stop. So at some point, we started to worry about the cameras because we didn't want to have just white images. We were running around making sure everything went fine. And somebody at some point said, "Oh, it's an X flare." And we were so happy and excited. And after we calmed down a little bit, we went and checked and saw that every other observatory got it too. So this makes it the best flare in solar history.
Great, thank you, Lucia. One of the things that was particularly exciting was that IRIS had saw the flare. So we're going to be talking to Adrian Daw, who's going to tell us a little bit about that mission.
Thank you, Karen. IRIS is a small explorer class of instrument, and it is the most recent addition to NASA's fleet of solar observatories. It is led by Lockheed Martin out of Palo Alto, California, and it looks in incredible detail at some particularly important layers of the solar atmosphere we'll be talking about later. And because it looks in such detail, much like a microscope, it can't look at very much at the same time. And so it's very difficult to know across the whole sun where the action is going to be. And through a lot of planning and a little bit of luck, all these instruments were able to catch this extraordinary event. An X-class flare is you could think of X standing for extreme. It's the largest type of flare, the most energy, the most X-rays. It's just an incredible data set, and it takes, as I said, a lot of coordination and planning. And one interesting thing is that even if there were an instrument that could react and suddenly point to where a flare is occurring, that wouldn't actually do us that much good, because part of the most interesting part of the story is what caused the flare to go off in the first place and events leading up to that. And so but in addition to that, in order to plan our satellites, we have to get our commands up from the ground, and so NASA Ames, that does our mission operations for IRIS, they have to send out commands at least a day in advance in order to catch these events. So it's just a lot of really exciting data from this that we'll be showing you in a little bit later on.
So what's important is that this was, in fact, the first time IRIS has seen an X-class flare, and I'm pretty sure it's the second time it's seen a flare at all. Am I correct on that? Yeah, I'm pretty sure.
Well, yeah, there are a lot of different classes of flares, so it depends how small you want to count.
Well, the first X-class, so it was a very big deal and very exciting. And to tell us a little more about why it's so exciting to have all of this stuff at once, we have Jeff Newmark, who's going to talk to us from NASA headquarters.
Hi. So as we've heard, this is the best observed flare that we've had to date. What do we mean by that? What does the best observed mean? Well, flares and actually the atmosphere of the sun in general are extremely complex. And studying this region, it requires understanding from the small scale to the large scale, the overall to the whole sun. And we actually can't do this with any single instrument. What we use is a fleet of instruments. So we've developed what we call the Heliophysics System Observatory, or HSO, as you see in the graphic here. This is a whole suite of missions from NASA and also our partners around the world, as well as we supplement this with ground-based, as you've already heard from Sacramento Peak. What this fleet does is it works together, and it allows us to look at the entire life cycle of a flare, the precursors, what happens before the flare goes off, what releases the energy during the flare, and what are the effects of the flare. These parts of the sun that we're looking at vary in temperature from 10,000 degrees to 10 million degrees. So we really require this entire huge fleet of instruments to understand this all. Next, of course, why do we care? Why do you care about flares? Well, this is a long-standing problem in solar physics. And really, what causes this catastrophic release of energy, and then what happens? Well, flares are actually one part of what we call solar storms or space weather. Space weather affects actually throughout our technological society and affects humanity. What we see with the HSO are not just looking at the sun and seeing the light, but we actually track the accelerated particles and energy from this flare. We see it going into interplanetary space, and we see it through as it hits the Earth and near-Earth satellites. We've seen this through a number of our things, and you'll hear a little bit more about these today. So this energy and accelerated particles, they have significant effects on our technological society. They can cause radio blackouts. They can cause damage to our spacecraft. They can cause damage to our power systems. So we really care about understanding these space weather events. And it all starts with understanding of the physics of these flares. And so that's really what we're excited about today. For the first time, we're really beginning to build up the data set that allows us this full understanding. Okay.
Great. So Jeff just started talking about understanding the physics of the flares. And we're going to go through all these wonderful, pretty pictures of what was seen on the sun. But just to give you a little background first, we want to tell you about the physics of what's going on in the sun. And to tell you something about what the sun looks like and what people are studying is Albert Shi.
Thanks, Karen. Right, so what you find when we talk about all these different data sets is, as Jeff already hinted at, a lot of these different missions look at different parts of the solar atmosphere. So we really need to have an understanding about what we mean when we talk about the solar atmosphere. When we look at the sun in visible light, what you're seeing is the surface, what we call the photosphere. But above that, just like Earth's atmosphere, there are different layers which have different properties and different characteristics. Do we have an image of the... Thank you. So right above the photosphere, which has a temperature of about 6,000 degrees, there's a layer called the chromosphere. And the chromosphere goes through a temperature minimum of 4,000 degrees up to 10,000 degrees over a few thousand kilometers. But the interesting change happens in the next layer called the transition region, where it goes from the temperature of the solar material, the plasma, goes from 10,000 degrees all the way up to 1,000,000 degrees and hotter even. In the corona, we see temperatures regularly of a few million degrees, and in the hot material in flares, you can actually see temperatures up to even 50 million degrees. Very hot temperatures, and that actually points to lots of energy questions about where all this energy comes from the sun. In each of these regions, different processes occur And that's what these different satellites are looking at. But in the corona, what happens is that the magnetic field lines that are present in the corona actually can force the solar material, the plasma, around. And that's when we can see everything in these beautiful coronal loops and images I'm sure you've seen. And also, what then becomes really interesting is when those magnetic field lines interact with each other and they can get a flare occurring. And Sabrina will be talking more about that.
All right. All right, hi. So I get the fun part of this discussion. I'm going to talk about solar flares and how they occur. So as Albert hinted at, we have this very dramatic change in density and temperature between the surface layers of the sun and the atmosphere, or the corona of the sun. And so in between these layers, there's this struggle between gas pressure and magnetic field pressure for dominance. And this causes the magnetic field lines, or the roads along which the solar material is allowed to travel because it's a plasma, to become twisted and tangled as they pass between the surface and the atmospheric layers. So these fields, as you can imagine, become very unstable, and it takes a lot of extra energy to be able to maintain that balance between the turns and the twists. So imagine, if you will, if you have a wad of rubber bands in your pocket and you've been playing with it and been twisting it and just turning it into all sorts of shapes and having it just twisted up. And then you throw it on a counter. What's going to happen is it's going to unravel because there's a lot of energy that's been released. And this is very similar to what happens with the magnetic field lines. Your hand is very similar to the convection zone of the sun, where the magnetic fields have been twisted and shaped. And so when they come up into the atmosphere, they're allowed to release. Except they do it much more dramatically than rubber bands on a counter. And this is done through a process called what we call magnetic reconnection. And what you end up with in the end, after the magnetic field lines reconnect and change, you get this nice organized slinky of loops. And it's really quite amazing that that even happens. But all of that extra energy that was put into holding this mess of rubber bands in this unstable equilibrium has to go somewhere. It can't just disappear. And what you end up with is a burst of light, a burst of energy, as particles are slammed into the solar surface really hard and really fast. And it's that burst of light, that's what we're referring to as the flare. And for perspective, a typical flare, a large flare, especially like this, can amount to the same energy release as 10 million volcanoes. And to put that in perspective, if we lined up 10 million volcanoes in a row, you would end up having to span across 30 suns. So this is an incredible amount of energy release in just one little pocket of the sun. And so that's what we're studying, and that's why we're so excited that we're able to look at it with all these different instruments, because even though we know approximately what's happening, we don't know the exact mechanisms. How does energy get released? How do all these particles get slammed into the surface? And how does it even get triggered? So, Karen.
All right. So we have an understanding a little bit of what flares are. I like to go back to those rubber bands all twisted and turned up. One of the things that all of these observatories are trying to untangle is what's going on in those rubber bands, what's setting it off. And we're going to now go through all of these missions that we're going to talk about today and say what little parts that they saw of this twist of rubber bands. And just to tell you all, we will be taking questions a little bit later on, so send your questions to #AskNASA, and we'll be throwing them out to our experts in a little bit. But in the meantime, we are going to talk about NASA's Solar Dynamics Observatory, and to handle that right now is going to be Jeff Newmark again at headquarters.
Hi. So the Solar Dynamics Observatory, or SDO, actually looks at the sun, and it looks at the entire sun all the time. We get images of the sun every second or so of the, and we look at the corona of the sun, especially with the SDO. And what this does is it gives us the global picture. We already heard, as Sabrina said, how these very small-scale features release this huge amount of energy. But we also heard about how this rubber band, the magnetic field, is being wound up. Well, this actually happens on a large global scale of the sun, and it's this global scale that SDO allows us to look at, because it's looking at all the time. And can you, while we're looking at this, if you can roll the movie, the SDO 193 movie for me, what you'll see here is exactly as you see the entire sun as it's evolving, and you'll see active regions, the bright areas are active regions. These are areas where the magnetic field, or this rubber band analogy that we've been talking about, is wound up very tight and it's producing a high energy state. And it's in these areas where we can get some of these large flares. And so this sees us before the flare happens, we're watching the sun. During the flare, SDO allows us to watch the response globally. And then after the flare, and there we go, we just see the flare occurring now. And then we can see afterwards what happens. What is the overall response to the entire sun to this huge event, even though it happens in the release of energies in a small area. And to give us some more details now about the small scale and how we focus in with our other telescopes that are like microscopes on the sun, I'd like to have pass it off to Lucia.
Thank you. So the Dunn Solar Telescope is special because it's the only ground-based telescope in this set. And we actually have the highest resolution, but only of a tiny region. So we can only see the sunspot. That's why we have to choose carefully where we point at. We used several instruments to get our data. They're called EBIS, FIRST, G-band imaging. And the reason for that is that we just want to have different solar layers. So we have several cameras with several filters. And as Albert told us, we can watch the chromosphere and the photosphere nearly at the same time. So these images are, I think, the first very high resolution observations of an X flare. And we can see amazing tiny structures in that flare, which will help us understand how the flare really evolves. We also have something which is called spectra. These are special measurements to get velocities, the temperature, and densities. And even more special are the polarization images, which show us the magnetic field. So flares only happen when the magnetic field changes. And for the first time, we might be able to get the magnetic field in a chromosphere to actually see these changes during the flare. And it's really great to have data from all the other observatories to get a three-dimensional view of all the different solar layers and also see the effects of the flare, while maybe we can also see the causes of the flares. And Sabrina can tell us more about what Hinode saw.
All right, thank you. So Hinode was a mission. It was launched back in 2006, nearly 8 years ago, surprisingly. Still going strong as part of the Solar Terrestrial Probes program. It's actually a collaboration between many international and domestic partners, namely JAXA, the Japanese Aerospace Exploration Agency, and NASA, and also the University College London, European Space Agency, Lockheed Martin, Smithsonian Astrophysical Observatory, NRL, the list goes on and on, many academic institutions. And why this is important is because this is a really big collaboration. We have 3 instruments on board, not just one, and they all operate independently, which makes planning observations tricky, especially when we're coordinating with all these other observatories as well. But it also affords us a lot of opportunities because we have such a big collaboration and we are able to collaborate across the board. All of the instruments have very different science goals, so it does make the plans complicated, but it does what we are able to do is see very different aspects of the sun with just one observatory. So I don't know if we're playing the calcium movie from SOT, but first I'm going to talk about the Solar Optical Telescope. We had several different images that the optical telescope took. For instance, we saw the chromospheric magnetic network with the calcium-2 images. And we were also able to look at the magnetic field with one of the filtrograms. And we're able to possibly see some of the surface evolution of the magnetic field, but stay tuned for that one. Then with ICE, which is the EUV imaging spectrometer, we're able to take 2D spectra of the sun looking at, there we go, there's at least the ICE images. So we're able to look at the sun in different layers with spectra. And what that means is we're able to see what the plasma is doing, the solar material, what it's doing, where it's going, how much of it is, and at what temperature it is at different layers of the sun, looking at different line profiles. So that's really exciting that we were able to see this flare, the whole kernel, the whole evolution of the flare with this instrument. And then with XRT, there's also a movie with the X-ray telescope showing the fields evolving. There we go, the fields evolving through the corona. So this is really hot temperature plasma or solar material. We're looking at more or less 10 million degrees, and you can see how the fields evolve and move upward through the atmosphere as the flare evolves. So basically with Hinode, we're able to see a lot of the evolution of the flare going from the photosphere up through the chromosphere and into the corona with one observatory. But the region that we're not able to look at as well is the transition region, or this interface region, where everything goes nuts. We have this huge increase in temperature, we have a drastic change in density, and that is what IRIS was really designed for, and that's why we coordinate so closely with them. And it's always exciting when we're able to get all of the instruments to even look at one flare altogether, but to have IRIS and all of these observatories to be able to look at an X-class flare, that's when we start having press releases. So with that, I'm going to turn it over to Karen to move on to IRIS observations.
All right, we heard a little bit about IRIS already, and that this was the first X-class flare it's ever seen. But Adrian is going to tell us a little more. One of the things that I think is particularly interesting about IRIS is that the area of the sun it's looking at is so dense that even figuring out what's going on in it requires this incredible amount of computational power. I mean, it just takes computer hours like you would not believe. And we have NASA Ames is helping with that, the University of Oslo is helping with that, and that is why it's been so difficult to see into this one region of the sun. Is not just because we have to have better and better telescopes, but it's so difficult to even untangle the information you get. So Iris is going to, not Iris, so Adrian is going to tell us a little more about IRIS and what it saw.
Well, thank you, Karen. Well, I should probably start with what IRIS stands for. It's the Interface Region Imaging Spectrograph. And the interface region refers to the layers of the atmosphere that Albert was mentioning earlier, the chromosphere and the transition region. So that's really where, moving away from the surface of the sun, the temperature shoots up eventually to millions of degrees. And it's an imaging spectrograph, like the ICE instrument on Hinode, and like some of the ground-based instruments that Lucia was talking about. And as Karen was mentioning, it specifically targets this thick region of the atmosphere known as the chromosphere. Here we're seeing right now a movie of the set of observations, and we just saw the flare go off there at the very end. If we run that again, I can explain a little bit. These imaging instruments, imaging spectrometers, have a slit, which you can see in the right frame is actually an image from the IRIS instrument, and that dark line is called the slit, and the light that passes through that goes to the spectrograph and gets split up by wavelength. And so those would be the two images on the left. We're looking at two different, well, we're looking at emission lines from ions in the solar atmosphere that are formed at different temperatures. And we know the wavelength that those ions emit when they're at rest. When they're moving towards us or away from us, the wavelength gets shifted to the right or to the left. Actually, I got that backwards. In this case, a shift to the left would mean that it's moving towards us, and a shift to the right means that it's moving away from us. And IRIS targets some specifically chosen wavelength regions of the sun in the ultraviolet. The chromosphere does emit primarily in the ultraviolet and emits most of the ultraviolet radiation that impacts the Earth and the near-Earth space environment. The flare frame, the pictures that we're looking at right now, and whereas in the previous set you saw how the image was scanning across the active region, Here we've just picked out one position and shown a few steps in time, right when the flare occurs. And I wanted to, if we can play that through a couple times, I wanted to point out some of the excitement. One is that you see only in one frame there appears down at the bottom there a little blip that I circled, and that is an extremely fast moving piece of solar material at chromospheric temperatures. It's moving at about 1,000,000 miles an hour. And the only way we know that is because we caught it in the spectrograph and we're able to measure its wavelength shift. And then in a couple frames later, you see another area that I've circled that starts to get brighter, and that is some extremely hot material. While IRIS is actually targets the chromosphere and transition region, it can actually image the photosphere as well. It also sees this extremely hot, high-temperature plasma of around 10 million Kelvin, which you typically only see during flares. And so hopefully this shows some of the power of the spectroscopy. IRIS has incredibly high spectral resolution, which means it's really able to provide unprecedented detail in terms of the motions and flows that we are seeing. You know, Hinode is another instrument that has the extreme ultraviolet imaging spectrograph on that instrument. Also looks at individual emission lines. The two instruments complement each other very nicely because Hinode sees primarily the coronal temperatures, whereas IRIS can look at the lower layers of the atmosphere in incredible detail, and at the same time see some of this really hot solar material that only occurs during flares.
Great. So we've just talked about one of the newest missions in the heliophysics fleet. Heliophysics, for those of you who haven't encountered the word before, is not just studying the sun, which is part of it, but also the entire Sun-Earth connection. So how what happens on the sun, things like these flares, can affect the Earth, can affect near-Earth space, and indeed the whole solar system, what is going on. So IRIS is one of the newest parts of our heliophysics fleet, and we're going to switch to something that's been up for 12 years, which is RESI. And Albert Shi is going to tell us what RESI saw.
Thanks, Karen. Yes, RESI was also, just like IRIS, a NASA small explorer and launched in 2002, and it's still going strong. It's led and operated by UC Berkeley. And fortunately for RESI, it's a full sun imager, kind of like SDO. And so for any kind of these coordinate observations, RESI is always looking and always ready to observe. Now, the question is, what does RESI observe? Kind of like many of the other instruments we're talking about, it also takes images and spectra, but in this case, RESI is looking in the X-ray and the gamma ray range. More energetic X-rays than the XRT instrument on Hinode, and then gamma rays going up to many MeV of energy. And why do we want to look there? The reason why is because flares, as Sabrina had mentioned earlier, release a lot of energy, and the surprising aspect of that is that up to tens of % of energy comes out as energetic particles. And by energetic particles, I mean both electrons and ions, such as protons and carbon nuclei and all types of particles like that. And so when those particles come down the magnetic field lines, they can interact with the atmosphere, and then we can see the signatures of those particles, and thus we can measure what's actually going on with this particle accelerator, the sun being the most powerful and efficient particle accelerator in the solar system. The result, the data from RESI, because we're imaging in X-rays and gamma rays, aren't as pretty as the intricate kind of and detailed figures we've seen before. But can we go back to the previous one, the previous figure? You can see for the RESI data, you can put it into the context of the other kind of observations that we get for the same flare. And what we can see in the RESI data is that there are right there on this image, in the kind of magenta purple spots, that is where energetic electrons are impacting the chromosphere. And the cartoon that you should have in mind is that there's this magnetic loop that extends into the corona, but the electrons come down and hit at the chromosphere, and that's where the bottom of the loop is. if you go to the next image, you can see that on the left there is where the electrons hit the chromosphere, and between them, you see the middle of the flare loop up in the corona, and that's where there's a lot of hot plasma. So on the left, we see the signatures of energetic electrons from the flare, and we can talk about their energy and how many there are. And on the right, we can actually measure with RESI the hottest flare plasmas, in this case about 25 million Kelvin, hotter than a lot of other instruments are actually even sensitive to. And that shows how much energy is being released, how much heating of the plasma is occurring during these flares.
Great, thank you, Albert. So the question is, we've just given you so much information about the different little parts of the flare, the different parts of all these rubber bands of energy and magnetic fields starting to come together and cause a flare. So what have we learned? People are going to be studying this for a while, but what are we going to be able to learn from this? Jeff Newmark, please tell us.
Well, first, I hope we've really been able to convey some of the excitement that we have of these observations. We've really seen that through careful planning and a little luck, of course. We got a tremendous data set. But as Karen just said, this is actually not the end of our work. This is actually the beginning of our work. Now that we have this data set, the teams here will be working together to actually analyze the data and understand what's next. We hope to learn what are the origins of the solar flares. How does the whole solar atmosphere respond to the sudden release of energy? And then what happens to the energy as it leaves the sun? The particles that Albert mentioned, the high energy particles, all this whole system. That's what we really need to work on, is modeling the system, developing our physics-based models that eventually, in the future, we actually hope to ultimately be able to predict these events. As I mentioned earlier, this is one part of the system of what we call space weather, and this really affects us, and therefore we really need to understand the entire system. This flare alone, of course, is actually not the end of all of our observations. We hope to continue to build and evolve our Heliophysics System Observatory as we learn more, figure out what gaps we need, what additional information we need to have to continue to further develop our models. And so we're really just excited now at the new start, at just a hint of what we can do in the future. And so stay tuned.
Great. Well, now is the time to start taking people's questions. Remember, you can send your questions to #AskNASA, and we will be throwing them out to our experts here. And the first question I have, I'm gonna start with Sabrina, since she talked about flares, but if other people have some information to throw in, they certainly can. The question from Lucian Moore, who has asked us on Google+, is, what connection do the solar flares have to the solar cycle? And then a little bit about what are the solar cycles too, you might tell us.
Okay, well, this is a really big question, actually. I'll try to touch on it a little bit. The solar cycle is basically where the sun goes from being quiet to being very active. So at about 11-year pace, we'll go from having very few active regions on the sun, or sunspots, to having a whole lot of active regions on the sun. And the sunspots are basically this concentration of magnetic field. And inside them, they're dark, if you look at them in visible light, because they are actually cool, but they're still about 4,000 degrees. So they're cool to the external surroundings on the sun, but not cool as to us. So they're still very hot. But if you look at sunspots in the atmosphere above the sunspot, you'll see all sorts of X-ray material, especially if you look at it with XRT, for instance. It looks very different than if you look at it with the surface temperature filter from SDO. So you'll have these dark spots, and above them you'll have these very bright regions in the atmosphere, and this is tracing out the magnetic field. And that is an indicator that the sunspots are really tracers of the magnetic field. And over about 11 years, the sun will go, like I said, from having very few sunspots to having a whole lot of sunspots. And when we do have these very big sunspots, we tend to have solar flares. And so whenever the sun is active and has a lot of sunspots and active regions on it, we do have a lot of solar flare activity. And right now we are coming over the maximum phase of our current solar cycle, and this is where we tend to start having these really big solar flares, surprisingly. So keep tuned. We'll keep having solar flares and hopefully keep showing them to you.
Great, thank you, Sabrina. Anyone else want to, Sabrina, anyone else want to comment on that, or we cover it?
We're good.
All right. Well, then I'll keep going because we have more questions. Dr. Weller at Dr. Weller on Twitter is asking us, can we get an idea of the scale of these flares? We're seeing these videos, we're seeing whole sun pictures, we're seeing small scale pictures. What is actually the size of these flares? Why don't I hand that one to Albert, please?
Well, it depends on what aspect of the flare. I mean, there are a lot of size scales at play. When it comes down to the actual magnetic reconnection, that can be happening on a very small scale. But once the magnetic fields kind of reconnect, once they create a new kind of geometry, everything starts to ripple out from there. The diagrams that we're seeing are what we usually talk as solar observers are on like several tens of arc seconds, which is the equivalent of several, maybe 10,000 kilometers on a side. But that's just what's happening kind of right at the flare. Once you get out of that, you get larger loop structures that get formed, and certainly once you get to larger, even coronal mass ejections, where a large amount of the atmosphere, a significant chunk of it just gets thrown out into space by a flare-associated reconfiguration of the magnetic field. That kind of huge structure propagates through the heliosphere, can actually reach us at Earth even. So there's a whole range of size scales that actually are important here. Well, you just touched on the #1 question we're getting that a lot of people are sending in. I'm going to pass this question to Jeff. We've heard it from at Christina Valentine. It's also come in from Saran Raj, but people want to know what would happen if when a flare comes towards Earth. Is there anything we need to worry about? What kind of precautions are in place? So maybe, Jeff, you can answer that question, because I'm sure there are a lot of people out there who are wondering that.
Sure. So the flare itself is this release of energy near the surface of the sun. Related to that, as I had mentioned earlier, these space weather events and something, as Albert just mentioned, the coronal mass ejections, or we call them solar storms for ease. And this is the bulk of material that's billions of tons of matter that's going millions of miles an hour, traveling out, filling up our solar system, in fact. And these regularly actually do hit the Earth. What this does for people on the ground, nothing. We're protected. We have a magnetic field, fortunately, that surrounds the Earth, and we have our atmosphere that surrounds the Earth. And this protects us here on the ground. However, the space weather, these solar storms, do have an effect above our atmosphere. They have an effect on our spacecraft in space, our astronauts who go into space as they leave the protective area of the Earth, as well as our communications on the ground. This has effects in the upper ionosphere, which is where our communication satellites, their radio waves travel through. It can affect power systems, as the largest of these storms do, in fact, induce currents on the ground, which can affect transformers. So there is a range of effects. Fortunately, we have, as I mentioned, the System Observatory, the HSO. We have a fleet of spacecraft that is actually actively studying these events to try and understand it, predict them, understand it, understand the effects, and give it to the people who need to mitigate these effects in the future. And so NASA works with actually all of our partners, in particular NOAA. The NOAA Space Weather Prediction Center is the official space weather agency for the United States. And we work with them on the operational aspects. We give them the science. They look at the operational impact of that. So we have this collaboration that is actively working this, the effects of flares.
Great, thank you, Jeff. I'm going to go off to Adrian. He wants to add one extra thing about what flares do at Earth.
I just wanted to add one little tidbit there too, which is that one thing that can be an effect that you can see from the ground is the incredible display of aurora at northern and southern latitudes. Completely harmless, but a very beautiful thing to see if you ever have the chance to see that.
Great, thank you. I have a question I'm throwing into the mix, which is that we have been talking a lot about the NASA spacecraft up in space that are looking at the sun. And one of the reasons we can get such a good view of the sun from up above our atmosphere is the atmosphere can affect what we see. It blocks some of the light. It can even make things a little bit fuzzy for us. But we've been talking about the Dunn Solar Telescope, the National Space Observatory's Dunn Telescope. And it's part of what has made this such a great, robust set of observations. So I want to ask Lucia, what can a ground-based observatory bring to this mix? What does it help show?
So first of all, we can help coordinate. So these observations happened because we wrote proposals to the satellites, and together all the teams decided, yes, we would like to observe or try to observe flares. And the second thing is the Dunn itself has a really high resolution. So if we want to study the tiny details of flares, we absolutely need the ground-based telescopes. And the third thing is the polarization measurements, which some telescopes can do. For example, Hinode can do it in a photosphere, but only the Dunn telescope can do it in a chromosphere for now. And we hope that NASA will launch the next big solar mission, which will also be able to measure that in a chromosphere.
Great, thank you. We have a very NASA-specific question. The question from @Shadow404 is, can Voyager detect solar flares? Jeff, do you have an answer for that?
Well, Voyager actually can indirectly detect these solar storms. It's not the flare itself. Of course, as I've been mentioning, it's these storms, these materials that travels out. The largest of these, in fact, do travel across the entire solar system, to the edges of our solar system. And in fact, when Voyager, as it is at the edge of the solar system, can look at some of the effects of this and how these how these storms, the magnetic field in these storms, how it modulates particles. So while they can't see directly the CME, it can actually see some of the effects that the CME has in Voyager.
Great, thank you. Sabrina, I also want to go back to something you talked about. You were really talking about how Hinode can see magnetic information about what's on the sun. And we've sort of flirted with this idea that magnetic fields and how they move has something to do with flares. But maybe you can tell me why the magnetic part of this is so important, and why it's important that we be able to look at that, not just these pretty images, but actually be able to understand magnetic fields on the sun.
Well, that answer is very easy, because it's the magnetic field where the energy is stored. So if you could possibly bring up the picture from SOT that shows the magnetic field. Can we locate that? Maybe, possibly. Well, imagine, if you will, a black and white image, and in one part of the image we have a very dark region, and in the other part of the region we have a very light region, so it's black and white, and then it's very linear in between. You have a nice line in between, a boundary, and that indicates where the magnetic field is coming out of the surface of the sun and going back down into the surface of the sun.
Well, yes, yeah. That was it.
Okay, sort of. This is the calcium image. So this shows what's happening in the chromosphere. There's also an image of just the magnetic field. I know you have it somewhere in there. But that's good. That shows the sunspot, at least. So if you're able to see the movie, that shows how the field is evolving above the solar surface, and those dark regions are actually the sunspots. And if we have the magnetogram picture to show. Okay. Anyways, so where we have those sunspots, we have different polarities where like I said, the magnetic field comes in, out of the surface and back into the surface of the sun. And above there is where there's this concentration of energy. And so whenever those magnetic fields combine or reconnect and reconfigure, that's where we get this release of energy. So in order to track where the energy is going, where it is stored, how it is getting released, where it is ending up. We have to be able to look at the magnetic field measurements to know what it is that we're seeing and where the energy is going. So it's the magnetic field that is the tracer of the energy transport.
All right. One of the other things I promised we would touch on as we went through everything today was the fact that there were some other observatories that saw this too. I'd like to ask Jeff to tell us a little bit about what are the other things we watch. You know, we've shown you the pretty pictures, but there's a lot more we're looking for. We just talked about the magnetic data. Jeff, can you tell us what some of the other NASA assets we're looking at and what kinds of things they're looking to find out?
Sure. Well, as I mentioned, we actually associated with the flare were high-energy particles, and these particles go near light speed, just a little bit slower, and they were actually detected by our ACE and WIND spacecraft, which are part wave between the Earth and the Sun, and they detect high-energy particles that are traveling throughout the interplanetary medium that are going towards the Earth, and so those spacecraft saw it. We also track the coronal mass ejection, the solar storm that I had mentioned. We actually, our stereo and SOHO spacecraft actually can see storms as they travel throughout the entire space between the Sun and the Earth. They actually follow the material. They actually look at it going from over a number of days, in fact, from as the slower storm actually travels from the Sun and goes over the Earth. So we look at those spacecraft. And then our partner spacecraft, we have actually, as I mentioned, NOAA before. The GOES spacecraft, they actually look at the energy, the hard X-ray energy from these flares. We have partners from around the world, ESA spacecraft, such as the Proba 2 spacecraft, again, is looking at the disk of the Sun. So it's actually a worldwide, multi-U.S. agency-wide fleet that is actually looking at the Sun and the Sun-Earth connection, our heliophysics system.
Great. Thank you so much. And of course, we're taking your questions at #AskNASA. So go ahead and send us some more in. And if you're at all interested or confused about some of the images we showed of the specific missions, definitely send in some questions, and people will be happy to tell you more about their particular piece of the pie and what they saw. Jeff just told us again about the entire Heliophysics Systems Observatory, how all these spacecraft work together to create a big puzzle. And we've also been talking about the newest part of the fleet, which is IRIS. And so I want to talk about that a little more. I want to talk about looking at this one region of the Sun that has not been examined as well before. And Adrian's going to tell us a little more about that.
All right. Well, thank you, Karen. Yes, IRIS, I mean, it's looking just at incredible detail spatially and spectrally at the ultraviolet light in the chromosphere. And Karen mentioned earlier how difficult it is to understand what we're looking at because the interaction of the light and the matter is so complicated. The light, if you will, bounces around many, many times before it comes out and then enters our telescopes, and then we do all the instruments do their job and provide us such wonderful data from that. And you know, IRIS, as I mentioned, it's led by Lockheed Martin. Partner institutions include Montana State University, Smithsonian Astrophysical Observatory, University of Oslo, many scientists around the world working on understanding and interpreting that data. The light coming from the corona is a little more straightforward. So for many years, the community has been largely focused around understanding the corona, whereas a lot of action is going on in the chromosphere. It's not just our ability to have the fabulous performance of the IRIS telescope with all that information, but also the advances in computational power and also the computational techniques to understand that. And you know, I guess one point that's definitely worth noting is how much energy is actually going through the chromosphere. We've been trying for a long time to explain why the corona is heated to 1,000,000 degrees, and we know the magnetic field plays a very important role in that. But the amount of energy, because the corona is so it's not nearly as dense as the chromosphere, it actually takes very, very small fraction of the energy in the chromosphere to heat the corona. So, for example, a small fraction of energy leaking through the chromosphere, whether it be through wave phenomena associated with magnetic fields or through some of these reconnection processes that have been mentioned. It would only take just a very, very small fraction of that energy, and so that's also part of why it's such a complicated problem to try and figure out, because there is so much going on. We just need to account for as much as we possibly can, and that's what's great about having so many instruments look at all these different wavelengths of light to get the most information possible.
So out there in the social media world that we're taking questions from, you can send your question to #AskNASA. We're getting remaining concerns about the safety of Earth when there are flares. So it's worth talking about that one more time. Maybe, Jeff, you can tell us once again why or whether we're generally safe at Earth, and also how the fact that we're looking at all of this goes towards making sure of that.
Sure. Well, again, flares are extremely interesting objects, but I want to stress to all of our viewers that human safety on the ground here, we're fine. The sun has been doing this for the entire over 4 billion years of the sun and the entire lifetime of the Earth, and we're still here. So our safety, on the ground, we're fine. Where the effects of flares that can happen are in our technology, our technological society. That's where the secondary effects can happen. As I had mentioned, our communications, some of our power, as we venture to space, away from the Earth. But those can happen. But again, the way that we are mitigating it is by understanding it. As we develop predictive models, which we're getting much better, it's sort of like the Weather Service here and looking at hurricanes. Right now, we can protect, hopefully, better and better ourselves as hurricanes. 100 years ago, we never knew if a hurricane was offshore or not and where it was going. Now we can start to track it and we can begin to prepare. We're the same way. That's what NASA and our partners are trying to do with these solar flares, is understand when they're occurring, how strong they'll be, and then we can take the necessary precautions for our power grid. The power companies understand this, and they can take precautions with their transformers. Airplanes, they regularly divert flights away from the poles, which is where the effects are strongest, as Adrian said, the aurora. We are in constant communication with, through NOAA, through the operational aspect. So we indeed, by understanding the science, we go to prediction, and then the people who need to can take precautions, and they are regularly taking these precautions. So there's no need to panic or anything like this. This is understanding science.
Great, thank you. And then a more simple question, which is simply, if I can find it, which is simply, what will be the size of the sun at its peak activity? This was asked by @Yusuf Muhammad, and I'm going to throw that one to Sabrina, please, since she talked about the solar activity already. Oh,
Activity?
There you are.
What the question was?
It was the size of the sun at its peak solar activity, which I guess means, does the size of the sun change?
No, the size of the sun does not change during a typical solar cycle. If the question is what will be the size of the sun throughout its lifetime, then it will swell up as a red giant eventually in about 5 billion years or so, so we don't have to worry about it. But it will eventually extend out towards the orbit of the Earth. But that is not something that we're talking about here. When we're talking about the activity of the sun with regards to solar flares, the size of the sun does not change. Over the solar cycle, the heliosphere size does change. Out where Voyager is, the heliosphere will expand and contract by a little bit. But overall, the size of the sun doesn't change.
All right. And now I'm going to throw out one because I don't know who can answer this question. We have a question from Angelic Mayhap, who is interested in something which is still a little science fiction-y for us, but I know people are actually working on solar sails, and they're being tested now. What would the effect of solar flares be on a solar sail? Anyone want to hazard a guess, or anybody know? Oh, come on, someone has to jump in, or I'm going to assign it to you.
All right, well, I'll
thanks, Jeff.
So, again, the solar sails, as you mentioned, Karen, we've actually flown. Japan has had a mission, and we've had a mission to small missions with small sails for testing. And these have, the flare itself, again, the light is really not going to have, they're very short-lived. It's really not going to have much of an effect on the solar sails itself. The solar storm as it comes by, again, I think that the relative change is probably not going to have much of an effect because it's very quick, and it's not going to, the actual change in pressure, even though these sails are very thin material, is probably not going to have much of an effect at all.
Well, thank you. We have actually come to the end of our hangout. I want to thank everyone for participating and everybody for watching. We are going to finish up with one nice movie of all of this imagery all together. Thank you so much for being here.
On March 29th, 2014, an X-class flare burst off the sun and vaulted into history as the best observed flare of all time. The flare was witnessed by 4 different NASA observatories and 1 ground-based observatory. Each telescope captures a different aspect of the flare at a different height off the sun's surface. Working together, NASA's heliophysics fleet will help scientists better understand what sets off these large explosions on the sun. These images were taken using NASA's Solar Dynamics Observatory, or SDO. It specializes in capturing images of the entire sun at once. A close-up shot captures some detail, but not at extremely high resolution. IRIS watches a range of layers in the sun's lower atmosphere. IRIS follows a well-planned schedule to observe small areas on the sun in high resolution. It was fortuitously pointed on this active region of the sun in the hopes of catching a flare, and this is the first X-class flare seen by the spacecraft. The RESI spacecraft can only see material at extreme temperatures on the sun. To RESI, a flare looks like 3 pockets of heat in a triangle formation. There are 2 points on the bottom, showing the foot points, and a third at the top of the flare. The Japan Aerospace Exploration Agency's and NASA's Hinode shows a series of layers in the sun's atmosphere. The images from Hinode's X-ray telescope show how material progresses from the lowest part of the atmosphere, called the chromosphere, upward through the heart of the flare, up to over 3,000 miles above the surface. These images were captured by the National Solar Observatory's Dunn Solar Telescope in New Mexico. The telescope can focus on only a small area at once, but it provides much higher resolution of each area. The March 29th flare fortunately coincided with the best time of day for viewing from the ground. When combined, this comprehensive view of one single flare will shed light on many future discoveries.